Hello everyone. Let me ask you something simple. If you try to add 2 apples and 3 oranges, does it really make sense? Not quite, right? Physics works in exactly the same way. We cannot add or compare quantities unless they belong to the same kind. This idea is captured in the principle of homogeneity, which states every equation relating physical quantities must be dimensionally homogeneous. That means the dimensions of each term in a physical equation must be the same. Only then can they be added, subtracted, or equated. For example, work and kinetic energy can appear in the same equation because both share the same dimensions. This principle ensures consistency across all of physics.
Now, why is this principle so important? First, it ensures that equations in physics are logically consistent no matter which system of units you use, SI, CGS, or FPS. Second, it prevents us from writing nonsense equations. Imagine adding velocity and force in the same equation. The dimensions don't match, so the equation is invalid. Third, it provides a reliable method to cross-check whether an equation is correct. And finally, it guarantees that physical laws remain universally valid, whether you measure in meters or miles, seconds or hours. Let's look at an example to see how this works. Suppose we have the equation Q equals W plus X. Here, Q is heat energy, W is work, and X is some unknown quantity. Now, the dimensional formula of heat energy Q is mL squared T to the power minus 2. The dimensional formula of work W is also mL squared T to the power minus 2. For the equation to hold true, the unknown X must also have the same dimensional formula, mL squared T to the power minus 2. As you can see in the diagram, each term points to the same dimensional form, making the equation dimensionally homogeneous. So where do we actually apply this principle? We use it to check whether equations are dimensionally correct, a powerful exam trick to verify your answers. It also helps us derive unknown formulas. By ensuring dimensional balance, we can figure out relations between quantities even without knowing all constants. It's useful in converting units between systems, like from SI to CGS. And most importantly, it allows us to approximate new relations in physics. For example, energy equations in thermodynamics or kinematics often rely on dimensional checks. Of course, no principle is perfect, and this one has its limitations. It does not tell us about numerical constants such as 1/2, 2, or pi. It cannot distinguish between dimensionless quantities that still carry units, like radian and pure numbers. Also, two different physical quantities may have the same dimensions, for example, work and torque, even though they represent different concepts. And finally, it cannot check vector directions, only magnitudes. So while it is powerful, it cannot completely prove a physical law. Let's quickly recap what we've learned. The principle of homogeneity says that every equation must be dimensionally homogeneous, meaning all terms in the equation must have the same dimensions. We saw the example Q equals W plus X, where Q is heat, W is work, and X must also have the dimensions mL squared T to the power minus 2. This principle is extremely useful for checking equations, deriving new relations, and converting units. But remember, it has limitations. It cannot handle constants, distinguish between certain quantities, or check vector directions. So, to sum up, dimensional homogeneity is like a grammar check for physics equations, ensuring that everything matches properly. I hope this gave you a clear picture of how homogeneity keeps physics consistent and meaningful. See you in the next session with another fascinating concept of physics.